All right. Let's interrupt those conversations and bring your attention back to the stage. I know you are all very fascinating people, and you will get more time at the end of the evening to continue those conversations with your neighbors. We will have the space until 9 p.m., so I hope you will continue these conversations afterwards. But now I would first like to thank Databricks for generously sponsoring this event and providing all the pizza that you all are eating. And also, let's give a round of applause for Databricks. Databricks is also providing our first speaker, Reynold. Reynold Xin is a co-founder and chief architect at Databricks. In the open source community, Reynold is known as a top contributor to the Apache Spark project, having designed many of its core user-facing APIs and execution engine features. Reynold received a PhD in computer science from UC Berkeley, where he worked on large-scale data processing systems. Today, he's going to be telling us about a new package called Koalas.
All right, can you guys hear me? I think I got the mic up already. Let me just do one thing to set this up. All right, done. Okay, all right, this is an interesting setup. I'll try to turn around, but I do have a demo in which I will need to focus 100% on my screen later. All right, can I get a show of hands before I start? How many of you use Pandas? Pretty much everybody. How many of you use Spark? All right, almost everybody too. It's great. Then to make this talk a little bit easier, I want to talk to you about Koalas today, which is a new open source project we created about 2 months ago. I want to give you half of the talk just a demo, because I don't think it's a better way to talk about this project than just doing a demo. A little bit more about myself, I already introduced, but the thing I'm probably most proud of myself is I deleted more code in Spark than I've added. So in the night, my net contribution goes to 0. I like pop a bottle of champagne, I'm like, great. Most of you probably know this already, Pandas. It was started about a decade ago and is now the de facto standard for data manipulation, basically for data science on Python, in the PyData ecosystem. There's a lot of functionalities in Pandas. Basic manipulation, what you do kind of relational SQL, time series analysis, a lot of different features, right? And Spark, most of you probably also know, sort of a de facto standard when you want to work with big data, whether you're doing data science, doing ETL, or doing data engineering. It was created by basically a bunch of Databricks founders, me, myself included, almost also a decade ago, though the first 4 or 5 years, mostly the academic prototypes. It has programming languages in it has APIs in different programming languages, Python, Scala, and R and SQL, and also Java. And as a matter of fact, on Databricks, we offer a cloud data platform, and we work with mostly organizations who work large-scale data in the cloud. On Databricks, Python is actually our #1 programming language. There's more Python users on Spark than Scala, which Spark itself is written in, right? And we work with a lot of data scientists on Databricks. And we see this happening over and over again in the past few years. A lot of the data scientists, it's sort of a new thing, right? This term didn't even exist maybe 5 years ago. They get educated by going through MOOCs, and more recently, universities started to offer the data science programs. And in these programs, they typically learn Pandas. Some data science programs will teach you R, but for the ones that teach you Python, usually start with Pandas. And you teach you then NumPy and all of the other stuff. And Pandas becomes sort of the toolkit. And you get into the workforce as a data scientist, you start, hey, I analyze my data set right now. And a lot of the data set are pretty small. It fits on a laptop. And Pandas works really, really well, right? It's the same toolkit you've been using. And then at some point, there's some variety of reasons. It could be because, hey, now I want to work with a larger amount of data. It could be because, hey, I have some production data set I'm not allowed to copy onto my laptop due to like GDPR, right? And you ask around as a data scientist, and the more senior colleagues tell you, hey, yeah, we have a Spark cluster. It's like sort of the standard way to interface with big data now. go use that. It even has like a DataFrame API in Spark. It's the same DataFrame API as Pandas. And then, so everybody's led to believe that. As a matter of fact, I myself, part of the problem, I basically designed the DataFrame API in Spark about 4 years ago. And I actually modeled it after the Pandas DataFrame API, but I added all the tweaks to it to make it work better for the big data ecosystem and for a lot of the people that are already familiar with big data. So it ended up looking something like this. I'm just giving you a little bit of a snapshot that what the Pandas DataFrame API looked like and what Spark's DataFrame API looked like. There are a lot of similarities. Pandas, for example, the way you refer to a column in Pandas versus in Spark's Python API is the same. But there's also a lot of, there's like big differences as well as subtle differences. For example, Spark's API, DataFrame API is immutable, which means you can't add a new column to existing DataFrame. You have to create a new DataFrame and call this with column API to add a column. Whereas in Pandas, you just sort of in place mutate it. And different ways of doing renaming, different ways of doing a lot of it. And I think sort of right before this talk, I was discussing with somebody, so why the differences, right? Why aren't two exactly the same? And I think it also goes to sort of the different use cases that people do. Like for example, I think in Panda, it's mostly used for exploratory data analysis, whereas the Spark ones often used both for exploratory data analysis as well as building sort of heavyweight data engineering pipelines. Where when you're building data engineering pipelines, you care less about verbosity of the API, but you care a lot more about, for example, performance, as well as is this safe? Is this reliable? Can I construct sort of correct programs? So a lot of the Spark API is designed in more that context. A different way to explain it is Spark APIs are designed by computer scientists who think in terms of abstractions. If you think, what do you learn as a computer scientist, sort of in your CS 101, right? Like programs are, you break them down into modules, have different primitives, and use primitives, and you compose of a bigger program. So in a way, that's how Spark API works. Here are different primitives, and with this like primitives, you can construct a bigger program. Whereas the Pandas API is sort of designed more from an end user's perspective, designed by statisticians or people who just want to write a bunch of data analysis in the beginning just for finance. So for example, the way you implement a cumulative sum, if you want to run a cumulative sum in Pandas, there's a function called cumulative sum, like CUM, SUM. All right, very simple. In Spark, we're computer scientists, of course. We can't just give you a cumulative sum. It's called window function. Hey, the same functionality exists in SQL. The way you can run a cumulative sum is you sort all of the data, and then you shift the data by one, and then you have sort of lilac function, and you can construct it. Right? It's doable, but it's a lot more verbose. And you can actually, I think, often construct more functionalities because it gives you more primitives, but it's just more verbose. All right. And we have seen enough data scientists struggle when they go from small data to large data. And we've gotten enough support tickets. We decided to do something about it this year. So we started this new open source project called Koalas. So in one sentence, it offers a Pandas DataFrame API on Apache Spark. It was only announced about 2 months ago. It's a pure Python library. The goal is really to make big data science easier to work with for data scientists that are already familiar with Pandas. And before I get into the demos, we'll talk very briefly about some of the design principles we're following here. The first is a little bit different from Apache Spark's API. The Koalas API is very Pythonic. Pythonic means very different things to different people. Here, basically, we want to follow as much of the conventions in Pandas as possible, right? Whereas Spark's API Spark created a single API that looks very similar both in Scala, Java, R, and Python, which makes it maybe a little bit different in Python versus Pandas. The other ones, we really want to provide discoverable API for common data science functions. This is what I'm talking about. If you want to run a cumulative sum, we'll give you that function. You don't have to think about how do I construct it based on a couple different other primitives Spark offers. The third is we really want to work better with the API documentation here. It's actually pretty easy because a lot of the APIs are exactly the same as Pandas, so we just copy paste the doc from Pandas. For those of you that have seen the Spark API doc, let me show you what the Koala API doc looked like. All right, here. It looks exactly like what you would expect from a Python project. For example, let's go into series. Let's go into its alpha. And we have sort of learned from Pandas. We want to give you examples because examples are often the best way to understand functionality rather than reading what exactly it means by the first sentence or the second sentence. So almost every function comes with its own examples. Right? But there's something that's pretty unique to sort of big data. We want to give you guardrails to also prevent you from shooting yourself in the foot. When you work with a very small amount of data, it doesn't quite matter if you do something stupid because it's probably going to complete. And it won't cost you that much. You're just running on your laptop. Like what else are you doing? Your BitTorrent process could slow down a little bit in the background. But when you work with a large amount of data on a cluster, doing something stupid could actually cost you a lot of money, right? Or your company a lot of money. So we want to actually build in a lot of the guardrails to make sure you don't sort of just fall flat on the face. Last is want to be able to sort of have high test coverage and also be lean and move fast. So we're actually doing weekly releases with the project right now. And now let's go into sort of maybe the main part of it, demo. So for the first time, I'll be doing demo by actually typing everything myself without pre-typing everything in a notebook. So I have a Jupyter notebook here launched. This runs entirely on my local laptop. What I've done is I've taken an open data set, San Francisco Fire Department data set, that basically recorded all the fire calls you make to 911. And I've loaded in with the Koalas API. So the way you get started with Koalas, you could import databricks.koalas as KS. And then KS is basically similar to your PD, your Pandas package. And a lot of APIs are just there, and they have exactly the same signature as the Pandas one. For example, the way you read in a CSV is just read CSV, and you pass it in, and it's the same parameters you have in Pandas, right? I'm not going to run the Pandas version here because this data set is actually somewhat slow. It takes more than a minute to load in Pandas, and I preloaded it in Koalas. And this one thing is different here, which is, I will get into it later, but effectively Spark is lazy. Get to that later. So I added an explicit .cache to materialize the data in memory, so it becomes faster later. But first operation I've done is data.shape, pre-type that. This is exactly the same as Pandas DataFrame.shape. It tells you how many rows there are and how many columns there are. So it's 40 columns because I've capped the number of columns I have to 40. And there's about 5 million rows, so 5 million phone calls to 911 about fire department. All right. Now, let's just take a look at what this is. So this is a Koalas data frame. It is back under the hood by Spark. This is not a Pandas data frame, right? But it has very similar functionality as a Pandas data frame. You would run something, and it would show up to render it in Jupyter Notebook. And here's all the columns. Now, before I go deep into the demo, you can see there's a column called receive date time, and there's a column called response date time, and there's another column that's not showing up here called on-theme date time, which means when did the fire truck arrive. How many minutes do you think it takes on average for San Francisco Fire Department from the time they receive a call to the time they have a fire truck at the location of the call? 7 hours. Hopefully it's faster than that. 10 minutes. All right, we'll find out. All right, I'm not going to tell you right here. But say I'm a data scientist. I got this data set, right? It's actually it's an interesting data set because it's medium sized. It is not so big that it's like gigabytes. It's not so big that you have to use it on the cluster. But it's actually somewhat slow to work with in Pandas because Pandas, everything's single-threaded, and sometimes you could run out of memory. right? But what do you do as a data scientist? One of the first things you want to do is like, what are the columns here? So like data.dtypes. It's going to show exactly the same way as Pandas. Shows you all the 40 columns, including what the data types is. Object basically means string in Pandas often. But you can see here are the columns, call number, and all that. Now, what does call type mean, right? Let's take a look at the sample data we have shown here. Call type is like medical incident, alarms, medical incident. So as a data scientist, often one thing I want to do with data is maybe get a little bit of a value count. And what this does is shows me what are the call types and count each call type. And you could do exactly the same thing in Spark. You have to call a group by, and then you do a count. And often, the first thing when I do a group by followed by a count is I realize it's not sorted, so I will have to sort it myself. The Pandas one is pretty nice. It just sorts it for you, which in 95% of the cases is what you want. Right? The Koalas does exactly the same thing. It does a value count and sorts automatically for you, so you can know what are the most important ones. Medical incident, that's actually the number one reason people call the fire department. And what's the least likely one? Lightning strike. Right. Now, but what if you want to put this in a dashboard, you want to like email somebody something? Sometimes it's better to have a chart, right? When you work with Spark, it's kind of a little bit annoying to create a chart. Often I see people sort of shrink their data to a smaller size, export it to Pandas, and then call Matplotlib to do it, right? But there's actually this pretty nice feature in Pandas, which also exists in Koalas, that it's called plot. And let's say I want to create a bar plot. Here we go. Now you get a bar chart in one line of code. You can see medical incidents. This is now a little bit easier to visualize. You can send it to your friends or your boss. Right? Now, what's up with this neighborhood? I'm curious about San Francisco. Like, where do you think it's more fires happening? Let's just replace call type with the neighborhood column. See what happens. Tenderloin has by far the largest number of calls, and it's followed by Soma, is where we are, in the Mission District. Can you guys see this okay, or do I need to zoom in a little bit? One more level. All right. Now, the other thing that's pretty important for data scientists is to understand most data are messy. And often you don't have sort of clean data. Sometimes value might be missing, right? Like that's a very important thing. As a matter of fact, I think probably a third of the data science I talk to, like what's your most common operation, is to look at what's the null count or what's the invalid data count. And you could actually do this thing called NA, which gets applied to all the columns and tell you whether each of the values, if they're false, it means there's a value there. If it's true, it means it's missing. But this is not very readable, right? Why, if you just call sum here, you actually show you basically for every column how many missing values there are. You can see for the received date time, you always have an entry for the data. The other one is for the on-theme date time, there's actually a lot of missing values. Probably because the fire truck was either never sent or they've never made it because of traffic. Now, if I want to calculate the delay between so if you get a call to the point you actually send a truck there, I can't work with the data in which there's no sort of on-theme date time, so I have to drop it. And it's pretty easy to do in Pandas. It's called drop NA. All right, and then you can drop, for example, just a specific subset of it. And in this case, we would want to drop this specific column. And let's just assign it back to data. Let's just drop it as well. Okay, now let's do the same thing. See if I get a bunch of zeros now. I should expect for the received datetime and on-scene datetime to be both zero this time. Yep, 0 now. So I dropped all the rows that didn't have a time specified. Right, now let's take a look at these 2 columns. It's the same Pandas syntax. Oops. Oh, I have an extra. Now the screen's off. And recording stopped. Let's try this again. Usually something else fails, not because of the AV setup, once you start. Do you come back up? Let's try a different dongle. Awesome. Cool. All right. Okay, so you can see there's 2 columns. Now, what I probably want is to get the delta between the 2, right? I want to figure out the delay. Now, one thing is, I just look at one column for now. This is a bunch of strings. So I can't exactly subtract strings. They don't mean anything. You got to convert it into timestamp or datetime. How do you do that? The one thing here, Spark DataFrame convert string to day. If you open it, the Stack Overflow, here you can cast and you can specify basically the date format explicitly. So I could take a look at this and figure out, specify the date format, right? Now, take a look at Pandas. Pandas convert string into timestamp. One function pop up to datetime. It turned out there's this magic function in Pandas that a lot of people have worked on. They added a gazillion different rules to just automatically recognize what the string formats are and try to infer what most likely this, what the format is for the timestamp. Now let's do the same thing. What did I search for? I searched for Pandas. Let's just change it to Koalas. All right, same function popped up. Same thing. Let's try, see what happens. All right. So let's say receive. And let's convert it to datetime. Let's try what happens. All right. Hopefully it works. Oh, something should pop up. Okay, the strings now look a little bit different. Let's scroll down.
Would you mind restarting the QuickTime recording?
Oh, yes. It would be 2 files though. All right. Okay. All right, now it's actually a datetime object. So the toDatetime kind of just magically takes a string and infers what it is. It's actually running slower than the Spark version if you explicitly specify what the format is. But if you're a data scientist working with some data, you're not trying to optimize the hell out of the performance of this job. You're just trying to do some exploratory data analysis. It's super convenient, right? Now, let's then just convert everything to datetime. What's the other column? The other column is on theme, datetime. let's say arrive. Oops. Arrive equal also ks.toDateTime data. All right, let's do that. And then let's take a look at this. Right, this operation is kind of slow because it's very CPU intensive. It is literally trying a lot of different ways to parse data under the hood. Okay, so now we have this pretty nice thing. And then we could also do data delay equal data arrive minus data receive. And then take a look at delay. All right, so what is a unit? It looks like seconds, right? 23:59:05. So this fire call took them about 6 minutes to arrive. The next one took them also about 6 minutes and 10 minutes and all of that. All right, but what's the distribution? One of the things you probably want to do is describe. And what it does in Pandas, in case you don't know, it computes you what's the minimum value, what's the maximum value, what's the 50 percentile, 25 percentile, 75 percentile. Now, it is actually somewhat intensive because you're trying to do kind of this compute percentiles or expensive operation on sort of even medium-sized data. Now, one of the things is, I tried running this on Pandas. It didn't actually complete after 12 hours, so I stopped it. The one thing that's a little bit nicer is with Koalas, you could actually leverage all the cores. So in Pandas, you run a single threaded. With Koalas, because it runs Spark code under the hood, it can at least leverage all your cores on your laptop. Right? So the laptop, I think, has like 8 cores, maybe 12. You see a lot of Python processes running in the background. Now, it's still not quite fast enough because this has just happened to be a very compute-intensive task. So what I've done is just like what every data scientist would do, hopefully, is, hey, why don't I run this on a cluster? So I have a cluster here with a terabyte of RAM, 136 cores, all right, that's lunch. Costs you very little to actually do it. And then let's try run. I preloaded a data set already. Let's just try run this. Done. 1 second. All right. So this is how many rows we have, and what's the average? Average is 500 seconds. It takes 500 seconds for San Francisco Fire Department to get to the point of the report. All right. I don't know why this is actually minimum value less than 0. It probably means there's like some data cleanup problem. That's something you should look more into it. And if you look at the 75 percentile, it's also about 500 seconds, like 578. But if you look at the max, it took hours, right? Days, maybe? I think it's hours. Right, well, actually, it might actually be days. No, but often you are not, as a data scientist, probably not looking at so what's the worst case and what's the mean. You typically often, when you talk about SLAs, like response time, you care about like 95 percentile or 99 percentile, right? So the same thing you can do with just like Pandas, you can specify the percentile this time. So you can see in the 90 percentile time, basically in 99% of the cases, the response time is actually less than 2,000 seconds. It's pretty decent, given the traffic situation in San Francisco. All right. Now, there's a couple other features I want to show you. We didn't want to just stop at Pandas. We want to really understand how people use the big data and make things easier. And Pandas is not exactly just a boundary. Now, one thing we think a lot of people do is also SQL. It is, depending on what you do, sometimes you might know that specific operation in SQL really well, whereas you don't actually know what's the API in Pandas or Koalas or Spark. So we actually integrated with Spark SQL, but we went a step further. We made it a little bit easier to interoperate. So you don't have to create, for example, like how do you go from a data frame to a table in SQL, right? The way you can do that in Koalas is you just specify it with the curly braces. Like I have a variable called data, if I just curly braces it, and I put it in SQL. And I could also use like other variables I define in Python. Now I could just run the SQL query. For example, I really am curious what the hell is going on with lightning strike. You can see they almost all happen on the west side of San Francisco. And you could run, for example, what about average delay in the different parts of the city? If you really worry about fire, don't go to Treasure Island. And as you can expect, like where's Soma? Soma's actually pretty good. Takes about less than 10 minutes for fire trucks to arrive. Okay, so here's the demo. Hopefully you get the sense of the purpose of the project just from the demo. Just to tell you a little bit more, we're doing weekly releases right now. We have implemented, I think, about only 30% of the functionalities of Pandas, but it's the 30% that everybody uses. We are rapidly adding a lot of functionalities. And there's also things that we have done specifically for big data. Like, for example, there's ways of reading, but easier way to parallelize Parquet reads, and easier ways to actually read this new table format called Delta, which is becoming the standard now for a lot of the big data storage. And we also integrate with MLflow, so you could now run, for example, TensorFlow models and directly apply them to a Koalas data frame. Right? And the project's only 2 months old, but there's already 300 patches to it. It's more than one a day. A lot of them are coming from sort of just the general community. It's now like Databricks engineers writing code. Like we do have engineers full-time working on it, but a lot of functionalities are contributed by sort of external community members. For example, the plotting functionality you saw is contributed by sort of a really nice contributor out of France. There's the PyPy, sort of Python package index download stats I show you on the screen here. You can clearly see data scientists don't work on weekends. But it's sort of growing. It's actually going over 4,000 downloads every day on PyPy. So there's a lot of demand. People really, I think, like this. You have a question?
Talking about MLflow, or are you just talking about the general concept?
Here I'm actually talking, there's literally a function that takes an MLflow, a model-defined MLflow, and you can apply it to the data frame here. Yeah. So go start on GitHub, and we love contributions. If you try something, it doesn't work. I think the project is still pretty rough. It's very early. It's only 2 months old. But one good thing about open source, you can actually contribute to it and to make your own life easier. There are some big differences, I think, also between Pandas and sort of, Koalas. And some of it, I think, is out of necessity. One of the things is Koalas is actually lazy by nature. What that means, although you probably can't tell, because every time it looks like data just being rendered when I was in the Python at Jupyter Notebook. But what we do is, if you explicitly name the variable and basically the repo HTML or the repo string is called, we actually compute and we materialize, run compute to show you the data. But if you don't, we actually don't run any computation. So we try to delay computation as late as possible to give Spark, query optimizer, the opportunity to see the bigger part of what you're doing so we can optimize it better. Like, for example, if your first step is to load in the entire data set, and the second step is to filter it down to just 2 rows, there's actually no point materializing the entire data set in memory. And this is what the laziness gives you when you work with bigger amount of data. When you work with a very small amount of data, it doesn't really matter. The other big difference is Koalas data frame, just like Spark's, doesn't have implicit ordering. In Pandas data frame, everything's ordered. In Spark's data frame, it's actually not the case. You could explicitly order things, but there's no implicit ordering that's assigned to the data frame. Right. In terms of what's coming next, we're basically trying to add functionalities as fast as possible. I actually use it all the time. Whenever I see something I wanted that's missing, I either try to implement it myself or ask somebody else to implement it. But there's going to be more work on plotting. I show you bar plot. There's a couple other things in there. But we'll be adding more plotting functionalities specifically for big data. because you don't want to be loading all of your data onto a single machine and then plot it. You want to start doing sampling. You want to start plotting things that's more important. You want to get just the outliers, right? There will be more stuff about string handling, also time series analysis. And really, in a lot of ways, open source projects are defined by the community and the users. If you see something's missing, file a ticket on GitHub, or even better, go implement it. So just to wrap up, Koalas offers the Pandas API on Apache Spark. I think versus Pandas, it gives you a way that's more scalable. If you're just working with like 100 or 200, 2,000 rows, don't bother, right? Pandas is great. But if you want to work with medium-sized and large amount of data, give this a try. With Spark, I think it's much easier to use, especially for exploratory data analysis. And to get started, it is published to Python package index and also Conda. So just do pip install Koalas or Conda install Koalas. And the GitHub repository is right here. Now, since I didn't put the slide up about this, we are hiring at Databricks. What we do is we build a lot of open source projects, but also we, more importantly, our entire business offer a cloud data platform. It makes data drastically easier to work with. And all of this are part of that bigger mission. If you're interested in contributing to that, we are hiring. And thank you. Any questions?
I will come around with the microphone, so keep your hands up.
All right. I could also repeat.
Saw you first.
Yeah, this is really cool. Thank you for the talk. There's an awful lot of stuff in the Python world that runs off NumPy. Mm-hmm. Have you thought at all about how you might share NumPy between the Python ecosystem and Spark?
Yeah. The answer is, have we? Yes, but we don't have a good way to do it right now. I think that things are just so different that it's very, very difficult. I don't have a better response than that. So who's working? I don't think anybody is.
Yeah, so you think it's a dead end, or it's because this seems to be something where you can actually share, sort of in-memory sparse matrices, for example. Seems like it would be really powerful.
Yeah, I agree. I just don't have a good grasp on it. Like I myself don't. I think part of the problem is I myself don't use NumPy enough. Like I use Pandas a lot. I understand what people would do with it. I typically stop at the numeric part. So there's fewer people. There's unfortunately a divide in the ecosystem or communities between basically the PyData NumPy, the more numeric part of Python, and the rest of sort of, hey, distributed computation and Spark and big data. I think it would, in order to actually maybe fix the issue or work on the issue you talk about, you really need somebody that understands both. And I myself just don't. And most of the people I work with, they in one camp or another, they don't usually even talk to each other. Often they hate each other.
Yeah, I've seen that problem too.
Yeah.
So, thank you very much.
I meant to applaud when you showed that you have examples for all that stuff. That was good. But my question is, what roles are you hiring for? What kind of people are you looking for?
Oh, everything. We're literally hiring in every department, like sales, engineering, support, lawyers, everything. But most people here are probably engineers. We hire a lot of sort of systems engineers that have more background in building, sort of like solving systems problems and also like operating maybe services. Like we have a product that's entirely SaaS, very different from maybe a lot of other companies in the space. But like, so it goes from like full stack engineers that could design brilliant UIs to people that could write Spark backend, right? So it's kind of everybody.
What about ex-physicists who are new to data science?
Yeah, the one thing, we have a customer-facing, like a field organization, they are more hiring for like data scientists to work with other companies, not necessarily to do consulting for them, but basically to guide them so they could get started on their own eventually. So that's not in engineering. Like, we build products for data scientists and data engineers, but our engineering org don't necessarily do data science and data engineering. But our field-facing org, like basically our customer-facing org, do a lot of that.